All right, so let's talk about one of the trickiest things in algorithms, recursion. You've got a function that calls itself. How in the world do you figure out how fast it is? Today, we're cracking open something called the master theorem. It's this awesome mathematical shortcut for doing just that. And hey, if you really want to dive into the nitty-gritty proofs behind this, we've got some extra notes for you down in the description.
And that right there is the big mystery of recursion, isn't it? A function's total work is all tied up in these smaller and smaller versions of itself. You can't just count the steps in a straight line. So how do you piece it all together?
Well, to even begin to tackle that mystery, we need to speak its language. We need a way to write it down, mathematically. And that language is called the recurrence relation. The best way to think about it, it's like a recipe. It's a mathematical recipe that tells you exactly how the total time to solve a problem of size n, which we call T of n, is related to the time it takes to solve those smaller pieces. Now, this recipe has just three key ingredients. A is the number of subproblems, so how many times does the function call itself? N over b is the size of each of those new, smaller problems. And finally, you've got f of n. That's all the other work you have to do. The chopping, the stirring, the combining, all the stuff that happens outside of those recursive calls. Okay, let's look at a famous example, merge sort. Its recipe looks like this. T of n equals 2 times t of n over 2 plus n. What does that mean in plain English? It means it splits the problem into two halves. That's the 2 and the n over 2. Solves each half recursively, and then takes about n steps, or linear time, to merge those two sorted halves back into one beautiful sorted list.
All right, so now we know how to write down the problem. Now for the fun part, the tool that lets us solve it like instantly. It's time to introduce the master theorem.
Believe it or not, this powerful theorem boils down to just two steps. It's super elegant. Step 1, you calculate this one special value, this critical value. Think of it as summarizing the total weight of all the work being done in the recursive calls. Step 2, you just compare it. You compare that value to f of n, which, remember, is all the extra work you're doing.
And this comparison, it's really just a showdown. It's a mathematical tug-of-war between the work done inside the recursion and the work done outside of it. We're basically asking which one is heavier, which one grows faster and is going to end up defining the algorithm's runtime when our input n gets really, really big.
And the great thing is, this tug-of-war can only have three possible outcomes. That's it. And each one points us directly to the final answer for our algorithm's complexity. So here they are, the three cases. Case 1 is when the recursive part wins the showdown. It's heavier, so it determines the runtime. Case 3 is the opposite. The combining work, f of n, is the heavyweight champ. And case 2? That's when it's a dead tie. The two sides are perfectly balanced, and whenever that happens, we just have to tack on an extra log n factor. Now, you're going to see this theta symbol, theta, a lot. Don't let it intimidate you. All it means is that the runtime grows at the same rate as whatever follows. It's just a mathematically precise way of saying this is the answer. Okay, that's enough theory. Theory is cool, but let's get our hands dirty and actually use this thing. We're going to walk through 3 examples, and you'll see just how easy this makes everything.
First up, let's go back to our old friend, the merge sort recurrence we looked at earlier.
All right, let's break it down. For this recipe, a is 2, b is 2, and our f of n is just n. So we calculate that critical value. It's n to the power of log base 2 of 2. Well, log base 2 of 2 is just 1, so the whole thing is just n to the power of 1, which is n. So the showdown is between n and n. Hey, that's a perfect match.
And because they're equal, that puts us squarely in case 2. The work is perfectly balanced, which gives us our answer, theta of n log n. And we're done. Just like that. No recursion trees, no complicated summations. That's the power of this theorem.
Ready for another one? Let's try this one. This recurrence here. This is the recipe for something like a binary search. You see, it cuts the problem in half every step, but then it only does a tiny, constant amount of work.
Okay, let's follow the steps again. A is 1, B is 2, and f of n is just the constant 1. So our critical value is n to the power of log base 2 of 1. Anything log of 1 is 0, so that's n to the power of 0, which is just 1. And look at that, we're comparing 1 with 1. It's another exact match.
So we're in case 2 again. The final complexity is our critical value, which was 1 times log n. So it's just theta of log n. And boom, we just proved why binary search is so famously fast in about 30 seconds.
Okay, last one.
For this final example, let's look at a case where the tug-of-war isn't a tie. In this algorithm, we're making 3 recursive calls on a problem half the size, and then doing some linear work to stitch the results together.
So A is 3, B is 2. Our critical value is n to the power of log base 2 of 3. Now, you can punch that into a calculator, and it's about 1.58. So we're comparing n to the power of 1.58 against our f of n, which is just n to the power of 1. It's pretty clear which one is bigger, right? That n to the 1.58 is going to grow way, way faster.
This is a classic case 1 scenario. The recursive work completely dominates. It wins the tug-of-war, hands down. So the runtime is just that critical value we calculated, theta of n to the power of log base 2 of 3.
And that's really all there is to it. You now have this incredibly powerful tool in your back pocket. You can analyze a massive family of these divide and conquer algorithms, and instead of wrestling with a complicated proof, you just do a simple comparison. So, now that you've got the shortcut, what problem are you going to solve with it first?